Hello everybody, this is Qingshan here. This is my first time to do this. Not my favorite way of doing lecture, but we don't have other choices. So this did give us some flexibility. So let's try it. Bear with me if something goes wrong, okay? So first, I want to talk about the exam. So this Thursday we will have our first exam, and since I'm out of town, so our grader will bring the exam to you. The exam has, as I said, that it is just looks similar to a regular homework assignment. So this exam has 5 problems. And you will have 75 minutes to finish it. It will be closed book, closed notes, and you are not allowed to use calculators either. So I also made sure that all the calculations are, simple. You don't need a calculator for those calculations. So now since I'm out of town, so I will not be able to do any office hours this week. So because of that, I commit to the emails. So if you have any questions, feel free to email me and I will respond as soon as I can. Okay. So you guys just received a homework set. As I already mentioned in class that the homework will be due on Thursday before you take the exam. So the homework will not be graded as usual. Instead, it will be graded just by completion. So it should be relatively easy to get the credits, but we still want to get the homework back, and encourage you to finish as much as possible, because it will help you on the exam. It help prepare you for the exam. So make sure you do work on the homework before you come to the exam. Okay, so today, so this is my plan today. So today we talk about some topics that are new, and then we will spend the other half of the lecture to review some basics. So the plan today is, first we talk about the symmetry rule for the Fourier transform. And then we talk about the differentiation rule. And for the latter half of the lecture, we will do some review. Okay. So last time we talked about the time shifting rule, right, and the scaling rule. So these rules help you to calculate the Fourier transforms, based on what you already know, and you can quickly find the Fourier transforms for some related functions without having to go back to the basic definition. So that was that's how these rules can be useful. Now, symmetry rule. Now what it is. So assume that ft, a function, has Fourier transform called capital F of omega. Now, so the omega, of course, is just a variable. Now, we can replace omega by another variable t, right? So it's just a regular function, like a regular function in the physical space. So the question is, if we view capital F as a regular function, what is the Fourier transform of this guy? That's the question. Does the Fourier transform of capital F have anything to do with little f? Now, hopefully it does, so we need to find out. Now, so the way we approach this is to write down what we know and then to derive what we do not know yet. So what is known now? Well, we know that the capital F of omega is the Fourier transform of little f, right? And which is the integral of f little t e to the minus I omega t dt. That's what we know. And also that since capital F is the Fourier transform of little f, now if we perform an inverse transform of capital F, we should get back to little f. So we also have this. Little f t is the inverse transform of capital F, which is 1 over 2 pi integral from minus infinity to positive infinity f omega e to the I omega t d omega. So this is what we know. So what we do not know, or what we want to know, is this. We want to find out the Fourier transform of capital F, which is minus integral from minus infinity to positive infinity capital F t e to the minus t omega dt. This is we want to evaluate this integral and what is it. Okay, so can we find the answer from what is known now? Well, it is clear that there is a lot similarity between these two guys, right? It appears that the first integral here is in omega and the second one is in t. It appears that the roles of t and omega are just swapped, exchanged. So now, how to figure out this? So since the role of t and omega are just exchanged, it seems that well, let's call this one 1, this is 2, this is my equation 3. So from 2 we have that integral from minus infinity to positive infinity capital F omega e to the I omega t d omega equals 2 pi ft, and we call this 4, equation 4. Now, equation 4, the integral in equation 4 is very similar to to the integral in equation 3. The only change is that the roles of t and omega are swapped. So to find the answer, it seems we just need to swap the t and omega in the answer. So now I want to write on the same page so that you can see the equation, and I will write here in this little corner. So compare 3 and 4. We obtain the following, or we draw the following conclusion, which is this integral dt will just be 2 pi little f of omega. I just realized that I made a mistake. The mistake is here in equation 3 here, that this is not the formula for Fourier transform. So for Fourier transform, we need a minus sign here. So we have a minus sign here. Now let me start over. Let me erase this guy. So now we compare 3 and 4. Compare 3 and 4. It seems that it seems that oops. So from 3 to 4, what is changed? Well, t is replaced by omega. Right? And so t is replaced by omega. If we replace t by omega and minus t, and minus omega replaced by t, we will go from 3 to 4. So I'm thinking of a better way to explain this. So let me try again. This logic does not work very well. Let me try again. So now let me copy it over. So these are our equations. Okay. Now, so equation 4 is known. Equation 3 is what we want to figure out. So now we rewrite equation 3. So f hat equals integral now ft e to the I t minus omega dt. Now, I did this. You see, I align omega with t, so then this t is aligned with minus omega. So then this is, now just compare these variables, know which corresponds to which. So equation 4 now suggests that this new integral should be equal to 2 pi f. Now, since t corresponding to my minus omega, so this is 2 pi f of minus omega. So that is the answer. So let's summarize. So if capital F omega is the Fourier transform of little f, which is ft e to the minus I omega t dt, then capital F Fourier transform is is 2 pi f minus omega. So that is the answer of this problem. Okay, now let's look at one example or application of this rule. The example is find the Fourier transform of 1. Well, we know that 1 is the Fourier transform of the delta function. So then the Fourier transform of 1 is 2 pi delta of minus omega. Now, because delta function is an even function, so it's 2 pi delta of omega. Now, let's look at one more example. So the Fourier transform of this function, 1 over 1 plus t squared, is pi times e to the minus absolute value of omega. And the question is, find the Fourier transform of pi e to the minus absolute value of t. Well, by the symmetry rule, Fourier transform of this guy will just be 2 pi, the original function, with t replaced by minus omega. Well, minus omega is, when it's squared, it's just 1 plus omega squared. So that is the symmetry rule. So next we move on to the differentiation rule. So let f hat be the Fourier transform of a function ft. Then what is the Fourier transform of f prime? So here f prime is the derivative of f. So the first derivative of f. We want to find out what is its Fourier transform. So again, now we start with the facts that are given to us. So these are known. Now f hat is the Fourier transform of f. So f hat equals integral from minus infinity to positive infinity ft e to the minus I t omega dt. So that is known. So, and we want to know is the following. We want to know the following. F prime derivative, which is the derivative of f. We want to find out its Fourier transform. So f prime t e to the minus t omega dt. And we want to know what is it. And in particular, okay, I apologize. It seems that I accidentally turned off the screen of my iPad, and then when it was turned off, the recording stopped. So I end up with 2 videos now. So I need to find out a way to stitch them together later if I can manage to do that. So now let me at least continue my lecture here. So we want to figure out what is this new integral here from what we know already. So now how to evaluate this integral? So if we are in a classroom, I would have asked you to suggest how we go forward. So, but now you guys are not in front of me, so I have to do it myself. So what to do with this integral? I would suggest integration by parts. I know this is also what many of you will suggest if we are in a classroom. So by integration by parts, so the integral here can be written as follows. dft. So I moved f prime behind the differential operator. So I have f now. So this by integration by parts equals to e to the minus it omega ft evaluated at minus infinity and positive infinity divided by integral from minus infinity to positive infinity ft d e to the minus it omega. Right? Now, what to do next? How to evaluate these functions at minus infinity and positive infinity? Well, it turns out you cannot unless we make some assumptions. So here, assume now ft vanishes at both t equals minus infinity and t equals infinity. That is, ft is a function that decay to 0 at infinity. So with such, we can continue the derivation. So integral f prime t e to the minus I t omega dt then equals to 0 minus here ft derivative of this exponential function gave us minus I omega e to the minus I t omega dt. Yeah. Okay. So this equals to this now equals to I omega times minus infinity positive infinity ft e to the minus I t omega dt. Now look closely at this integral. What is it? You will realize that it's actually the Fourier transform of little f itself. So the whole thing now is I omega times f hat, a function of omega. Now we can write this result as follows. So if f hat is the Fourier transform of f, then the Fourier transform of f prime equals to I omega f hat. So this is a very nice result. Also one of the most important results of Fourier transform, because what it does is it transforms a derivative in the physical space into a product in the frequency space. Now, product or multiplication is much simpler than taking derivatives. So that's the nice thing about this rule. So let me write down this observation. So Fourier transforms, it really transforms derivatives in the physical space into multiplications in the frequency space. This is a very nice result. Now, what about higher derivatives? So what about, let's say, derivative to the k times Fourier transform? What is it? Well, it turns out that higher order derivatives just leads to a higher degree polynomial in the multiplication. So the Fourier transform of the case derivative of f equals I omega. You just need to raise this to the k power and then multiply it with the Fourier transform of little f. That's it. That's that simple, you know. So now let's look at one example or one application of this. So in this example, the Fourier transform of ft, which is 1 over 1 plus t squared, is f hat omega, which is also given pi e to the minus absolute value of omega. Find the Fourier transform of minus 2t 1 plus t squared. We want to find out the Fourier transform of this new function. Well, how to do it? If you have done derivatives, or if you have done differentiation of rational functions, you should have noticed that this given function is not actually given. It's the derivative of the other function. It's a derivative of 1 over 1 plus t squared. So the Fourier transform of this new function now by the differentiation rule is 2 pi f hat of omega. So it's 2 pi. No. I made a mistake. It's not 2 pi. It's I omega f hat of omega. So it's I pi omega e to the minus absolute value of omega. That's it. That's the answer of this problem. So the differentiation rule, as I said, that it's very useful. It transforms something very complex into something quite simple. So because of this, Fourier transform can be used to solve differential equations. Today we will not go there, but when I come back, and the week after next week, or after the exam, so we will look at how Fourier transform can be used to solve differential equations. So we will stop here for the new materials. Now, some of you probably are wondering whether these materials will be on the exam. So the good news is no. The materials we talked about today, these new materials, that is these two new rules, the symmetry rule and the differentiation rule, will not be on the exam. But what we covered before today, what we covered up to Thursday, October 4th, will be or might be on the exam. So the exam covers material up to the class on October 4th. Okay, so now let's do some review. So when you set out to prepare for the exam, so you should think about what are the main materials or main topics that we have covered so far. So when I think of it, now I did not look at my notes or look at the textbook. I just think in my head what we have covered, what we have done. So here are the main topics that come up to my mind. So we talked about the complex numbers, right? Now, for complex numbers, what you need to know? Modulus, the face of a complex number, right? Euler formula. It's a very useful tool, so you should definitely know it. And also, one type of problem that we talked about is to find the roots of complex numbers. So when we introduce complex numbers, it expanded the concept of the roots. For problems that sometimes you normally do not think there is a root, will have a root in complex when we are in the domain of complex numbers. So be careful of this. In general, now a general rule is this: the number of roots will be equal to the degree of the polynomial. For example, a polynomial like this, z to the power 6, now equals, for example, whatever, minus 81. It will have 6 roots. So you should be able to write down the formula. What are the 6 roots? And you can see that if you only work with real numbers, this equation does not have any roots. But with complex numbers, it has a full set of 6 roots. Okay, complex numbers. Now, next big topic is the Fourier series. So here, what do you need to what do you need to know? Formula for coefficients. We also talked about the sine and cosine theories, cosine-sine series for even and odd functions. We also talked about cosine, sine series with phase angles. So how to find the, given a regular Fourier series, how do you rewrite it into a cosine or sine series, but with a phase angle? And we also did complex series, complex Fourier series. And we have also properties of Fourier series, like the Parseval equality. So next, we then, in the last few lectures, we did Fourier transforms. So we are still on this topic. We are not done yet. So for this one, what you need to know is to compute the Fourier transform of a given function. Okay, so now I just want to do one example. actually just go over one topic. So what I want to do now is to show you or to go over the basic steps for writing given Fourier series into a sine or cosine series with a phase angle. So let a function f be given and it has Fourier series as such. Right? So for cosine series, we want to write the function in this form. An cosine n pi t over L plus an angle phi n. Right? We don't know whether it's possible or not, but let's see. So by the sum and the difference formula, so this summation now can be written as follows: An cosine n pi t over L cosine phi n minus An sine n pi t over L and sine phi n. Now this series, now let's call this 1, let's call this 2. So the summation in 2 has to be the same as the summation in 1, right? So now compare 2 to 1, they have to be the same. That means that An times cosine phi n will have to be equal to little an, capital An minus capital An sine phi n will have to be equal to little bn, so that the series are the same. Now, from these two equations, I obtain that my capital An is the square root of little an square plus little bn square. And I also obtain that tangent of phi n will be equal to bn over an with a minus sign. So from this equation, I obtain that phi n will be arctan minus bn over an, or pi plus arctan minus bn over an. Now, exactly which value should phi n obtain depends on the sign of little an and little bn, because eventually you want to pick a value for phi n such that these two equations hold. That is, equation 3 hold. Pick a value for phi n such that equation 3 holds. So this is how you write a regular Fourier series into a cosine series with a phase angle. And the cosine series is given here. So you need to specify what is capital AN and also what's the value you take for phi n, and then write down the cosine series as it is in 1a here. Now, next let's see how you can derive a sine series. So we go ahead and write it in the form of a sine series. So now we expand it using the sum and difference formula. So let's call this equation 4. Now, compare 4 with equation 1. So let me copy over equation 1 here. So compare these two equations. So for 4 to be identical with 1, that's our goal. We needed the following relations to hold. First, Bn sine psi n should be equal to little an. That's the coefficient for the cosine n pi t over L. And Bn cosine phi n should be equal to little bn. Right? We need these equations to hold. Let's call it 5. Now, from this set of equations, we obtain that capital Bn, again, is just the square root of an plus bn squared. And the tangent of psi n is an over bn. Now, from this little equation, we know that the psi n will be equal to arctan an of little bn, or arctan an over little bn plus pi. Now, exactly which value you should take for psi n depends on the sign of little an and the sign of little bn. You need to pick a value for psi n such that equations 5 hold. Now you just need to decide which one of the value will give you the correct sign. you don't have to verify the actual value. So now, sine series, cosine series with a phase angle sometimes is useful because it has a single coefficient for each frequency. So that coefficient gives you the magnitude. So the complication is you have this phase angle to work with. Okay, so this is so one topic I wanted to go over in a little details. Let's see if there is anything else. Since I did this on my iPad, I did not look at my previous notes, so I'm just double checking to make sure I did not write anything wrong. Okay. Yes, I think for the cosine series it's correct. For the sine series, it is also correct. Okay. So now we have a little bit of time left. So let's see what else can we talk about. So let's work on one more example. So this one, find the roots of a complex number. I will just randomly make up an example. So let's say example, find the roots for z cubic equals I27. Okay. So for this kind of problem, the first step is to write the right hand side in the Euler form. So z cubic equals 27i, which can also be written as 27 e to the I of half pi. Right? So I'm just double checking. So on a complex plane, the imaginary unit is here, which has a phase angle of half pi. So I equals e to the I of half pi. So now let's assume that the z takes the general form, which is r e to the I theta. We need to find r and theta such that z cubic, which is r cubic e to the I 3 theta equals 27 e to the I half pi. Now from this equation we can establish a few relations. So we have, first, r cubic must be equal to 27. Also 3 theta must be equal to half pi. Here it's a little tricky here. Well, 3 theta can be equal to half pi, or anything or any multiple of 2 pi. Any multiple of 2 pi. Now, from the first equation, we obtain that r is just 3. Now, from the second equation, we obtain that theta is 1/6 over pi plus 2k pi over 3. Now, so you can see that the radius r only has one value, but the theta can have multiple values. And so these different values are indexed by a k here. So we need to decide the range for k. Now, what's the range for k here? Well, you only need to select k that give you distinct value for theta k. So for this, it's relatively easy. So k equals 0, 1, and 2. Well, when k equals 3, you will get back when k equals 3, now you start to have repeated phase angle on the complex plane. It will just repeat the previous phase angles. So here the range for k should go from 0 to 2. Hence, there are 3 roots for this problem. You can see that the number of roots equal to the degree of the polynomial here. So there are 3 roots. Z0 is simply 3e to the I pi over 6, and Z1 is 3e to the I pi over 6 plus 2/3 of a pi, which is 3e to the I 5/6 over pi, and Z2 is 3e to the I 1/6 over pi plus 4/3 over pi, which is 3e to the I 9/6 over pi. So these are the roots for this problem, 3 roots. Now I copy them over to this page because I would like to put them on the complex plane. So they all have radius 3, so they are all going to be on this circle. The first one has a phase angle of 1/6 over pi, so it's about here, Z0. The second one has 5/6 over pi, so it's about here, Z1. And the last one, 9/6 over pi. Well, 9/6 over pi is the same as 3/2 over pi. So it's here. So you can see that these 3 roots form an equipartition of the circle. And this circle has radius 3. Okay, so that's just another example. So I think we will stop here, and obviously you can see that this format of lecture has limitations, it's the first time that I do this, so I'm curious how does it work. So you will let me know when I come back. Okay. So if you have any further questions, don't hesitate to contact me by email. So I will see you in about a week. Good luck with the exam, with everything. See you later.